Hi everyone, welcome to the second part of Faster RCNN implementation, where we'll be doing a walkthrough of the PyTorch Faster RCNN codebase and understand all parts of it. Goal for this video would be to go through the entire Faster RCNN code and ultimately see how to fine-tune the pre-trained Faster RCNN model on VOC dataset. If this is the first video for Faster RCNN that you are watching, then I would encourage you to first see the previous two videos. If you are already familiar with Faster RCNN, then just the part 1 video will do. As for those methods which I have already covered in detail in previous video, I will just skim through them in this video. So let's begin with this one. We'll start looking from this Faster RCNN Resnet50 FPN method, which is part of torchvision. This method creates a Faster RCNN with Resnet50 backbone, and you can choose to get a pre-trained version which is trained on Coco dataset. Now since I haven't covered FPN yet, I'm not going to dig into exact details of it as we'll look at it in one of the upcoming videos. So for now, just think that rather than getting the features at one scale, like for VGG16, we were getting feature map output at stride 16, which we were using for anchor boxes predictions. Instead, now we'll pass the output of different layers of backbone to another module, which will compute for us new feature maps at different scales. So maybe at stride 4, 8, 16 and 32. We are going to use these feature maps for making anchor box predictions. And what this will give us is that for smaller boxes, it's better to take fine-grained features from an earlier level. So maybe at stride 4. And for larger boxes, we can use the features from a level with a larger stride. So the only thing that is going to change is that our backbone is now going to have this multiple feature map outputs. If we scan the code, we can see that this is exactly what happens. We create our Resnet50 backbone, and then this FPN feature extractor wraps the Resnet50 backbone with FPN class. Here the backbone that is passed will be Resnet50 layers. And notice the out channel argument that is passed as 256 here. We'll soon see where this is used. Inside this class, from the forward method, you can see that we get the intermediate layers of backbone, and this will return the feature maps at certain predefined stages of Resnet50 backbone, all having different channels. Then this FPN class is called, which ultimately using few convolution layers of its own, and these conv layers all have output channel as 256, which was passed as argument. Using these conv layers, the FPN class finally returns a dictionary, where all of the different stage feature maps are now of the same 256 channels. Apart from the already existing feature maps, the implementation here also adds a new key, which is pool, and its value is just obtained by applying a 2x2 max pooling kernel on top of the last feature map, so feature map of key 3. For those interested, this addition of new key happens within this extra blocks call at line 156. There is obviously a lot that happens here, and I didn't really cover everything. Neither did I go into details as of now, because for this video, the only thing that you need to understand is that ultimately, rather than getting only the last feature map, we get feature map at different scales. And the forward method of FPN will return a dictionary, with values being the feature maps at different stages, each having a different stride. Now going back to from where we started with this entire FPN call. Once we have set up a backbone that returns this feature map dictionary, the main model that is called is this Faster RCNN model class. So this is from where we'll actually be going into each and every method in detail. This Faster RCNN model class has three main components: backbone, RPN, and ROI head. And as input, it accepts the images, which is a list of image tensors containing all the images in the batch, and targets, which is also a list, but a list of dictionary for these images, with keys boxes and labels having the box coordinates and class labels for the ground truth boxes of these images. Let's start with the walkthrough from this class. The Faster RCNN Module class inherits its forward method from GeneralizedRCNN. And all the Faster RCNN class does is it instantiates the necessary components which are then used in the forward method of GeneralizedRCNN. These are namely the region proposal network, which consists of the AnchorGenerator, which will generate anchor boxes for us, RPN head, which is the 3x3 convolution and 1x1 prediction layers, so the RPN specific layers. The second component is ROI head, which comprises of the ROI pooling method, which here is MultiScale ROI align. And since I haven't covered ROI align yet, for now just assume that like ROI pooling, this will give us the proposal features given the box coordinates. Only the strategy of how it computes the proposal features will be different. Then this 2MLP head, which is similar to FC6 and FC7 layers that we implemented in the last video. So basically converting the proposal feature to a representation from which we'll be making predictions using our prediction layers, which is this box prediction layer, which is the classification FC layers and bounding box transformation prediction FC layers. Apart from ROI head and RPN, there's also this generalized RCNN transform component, which is going to handle things like normalizing the image, resizing the image, and so on. These are all the components that this Faster RCNN class will instantiate for us. But ultimately the class of interest is GeneralizedRCNN. So let's look at what's happening within its forward method. Starting with the arguments. And this basically will be the input that will be fed to the Faster RCNN model class in our training loop, which we have already seen. It will be images, which is a list representing the images in our batch, and targets, which is a list of dictionary, where the ith dictionary contains the box and label information for the ith image in the batch. Similar to last video, we'll be keeping track of shapes to ensure that we understand completely all the modifications that are going around. In this particular run of training, we are using a batch size of 2, and both images are of different sizes. The first image has 3 ground truth boxes, and the second one has only 1 ground truth box, as is evident from targets. After some validations, the first thing that we do is transform the images in the batch. And this is going to call the forward method of GeneralizedRCNN transform. Inside that, we loop over the images in the batch, and for each image, we normalize it using the provided mean and standard deviation, which by default is the ImageNet mean and standard deviation. And then we resize these images. The resize method calls this resize image and masks method. Ignore the masks part, which is present because the same code is supposed to cater to mask RCNN as well. As of now, we are only concerned with the resize image part, which is same as what we saw in the last video. Resizing according to min and max size, such that the smaller dimension is scaled to min size, but the larger dimension is not greater than max size. Min and max size can be provided as arguments to the Faster RCNN model class. And for fine-tuning, we'll later initialize min size as 600 and max size as 1000, similar to what the authors of Faster RCNN use. And remember, the way we do this is that we take the scale required to resize smaller dimension to min size and the scale required to resize larger dimension to max size, and whichever scale is lesser, we use that. So after computing the scale factor, we resize the images. Then we resize all the target boxes, because the target boxes up till now were for the original image dimensions. So we need to scale them also appropriately for this resized image. For this we get the resized image by original image size ratio and scale the coordinate boxes accordingly. All of this is same as last video. The only part that's going to be new is this batch image call. So up till now, our list of images in the batch could potentially have different sizes. Like in our example case itself, one is 800 x 600 and the other is 562 x 1000. But we need them to be mapped to the same size to call the backbone for the entire batch. Let's see how that is done. We first find the max across all dimensions amongst all images in the batch. So max along channel dimension is obviously 3, and for the other two dimensions, the max amongst the images in the batch are 800 and 1000. Instead of using 800 and 1000, the PyTorch code here modifies the value such that they are divisible by 32, which is the value of this size divisible variable by default. So the values that we get are 800 and 1024. Because 800 is already divisible by 32, hence no change happens for that, and 1000 will be converted to the next larger number divisible by 32, which is 1024. Hence we convert all the images in the batch to a 3 x 800 x 1024 tensor. And we do this by taking the already resized image and padding with zeros wherever necessary, using these lines of code. Just to give more clarity on what's happening here, assume after resize we have these two images. Then using the max along dimensions, we would create this all zero image of 800 x 1024. And then after filling the pixel values for both images from the top left corner, our batch will be these images. So batch images will essentially just map all of them to one common size by padding the resized images with zeros on the right and bottom wherever needed. Ultimately, transform method creates an ImageList object, which is a class having two fields, tensors, which will have the batch image tensors. So here it will be a 2 x 3 x 800 x 1024 tensor, and image sizes, which are the sizes prior to zero padding. We'll see later why we need these sizes. In our case, this would be 800 x 600 and 562 x 1000. So that winds up everything inside the transform call. Now the backbone call. For these batch tensors, so 2 x 3 x 800 x 1024 shape tensor, we call the Resnet50 FPN backbone. And like we had seen, this will return a dictionary of features with keys 0, 1, 2, 3 and pool. And they will all have these corresponding shapes. You can see that based on the size of batch images, the strides are 4 for the first feature map, which is the key 0, as our images were 800 x 1024, and the feature map dimensions for the 0 key are 200 x 256. Similarly, the stride is 8, 16, 32, and 64 for the other 4 keys. If it's not a backbone which has these keys, so assume we had just called our VGG16 model, which returned a single scale feature map, then PyTorch will create a dictionary anyways with just one key, which is 0, and its value will be the feature map that backbone returns. This allows us to specify our own backbone without FPN. So we can plug our own backbone here, say something like Resnet18 without FPN, and PyTorch will convert the backbone output to a dictionary, as that is what the later parts of implementation expect, that the output of backbone be a dictionary. Now we get into RPN. And before diving deep into RPN code, it's better if we spend few moments on how the AnchorGenerator is initialized, because that will ensure that we know why the shapes of prediction layers of RPN are such. When you look inside the Faster RCNN class, this is how the AnchorGenerator is initialized in there. Remember, we have 5 feature maps. So what this means is that the first feature map is responsible for making predictions for anchor boxes of scale 32, second of 64, third of 128, fourth of 256, and last one is responsible for making prediction for anchor boxes of scale 512. So each feature map is going to be responsible for anchor boxes of only a single scale. But for each scale, we are going to predict 3 aspect ratio boxes: 1:2, 1:1, and 2:1. This means that each feature map cell is going to generate predictions for 3 anchor boxes, which would be of single scale and 3 different aspect ratios. And just for clarity, say if instead this is how we had initialized, then this would mean that the first feature map is going to make predictions for anchor boxes of scale 32 and 48, second for 64 and 96, and so on. So each cell will now have predictions for 6 anchor boxes, 2 different scales, and each scale having 3 different aspect ratios. Okay, now going into RPN. And again, let's jump to the forward method. The forward method receives the image list, which has tensors as well as old image sizes, prior to zero padding, features, which is a dictionary with feature maps as values, and targets. For RPN, we don't really care about the keys, so we just get the feature map list and that becomes our features for RPN. So a list of 5 feature maps. Then we call the RPN head to get objectness and box transformation predictions for all anchor boxes. This RPN head was instantiated in the Faster RCNN class, where if we go, then we see that when RPN was created, we initialized RPN head here. And this is just a module consisting of RPN specific layers, which is the 3x3 convolution, 1x1 classification, and 1x1 regression layers. And in the forward method, we can see that we'll iterate over all the feature maps in the list, and for each feature map, it will return CLS logits and box regression outputs. So same as we did for our RPN in the last video, except here instead of doing just for one feature map, we are doing it for a list of feature maps. In the forward method of RPN, at this point, we'll get both objectness and prediction box deltas as a list of 5 values, each of these shapes. Box prediction deltas for each feature map will be 2x12 cross feature map height cross feature map width. That's because, like we saw, each individual feature map is actually going to cater to only 3 anchor boxes. So box regression prediction will only need to have 12 output values, which would be 4 transformation parameters for the 3 boxes predicted at each feature map cell. And that's also why CLS logits for each feature map will be of shape 2 cross 3 cross feature map height cross feature map width, as these would be the classification scores predicted for the 3 anchor boxes at each feature map cell. Then we call AnchorGenerator. The forward method of AnchorGenerator receives the image list, which has image tensors and original image sizes, and list of feature maps. Grid sizes will be the width and heights of all the 5 feature maps. Image size will be 800 x 1024 for this batch. Then from the image size and feature map sizes, we compute the strides for all feature maps along both the height and width. This line here then sets the base anchors. The implementation of anchors is same as our last video, where we first create base anchors that are zero-centered and then compute a grid of shifts to shift these base anchors respectively for each feature map cell, creating anchors for the entire feature map. But here we need 5 different base anchors because we have 5 feature maps. And each set of base anchors will have 3 boxes. Again, because each feature map is going to make predictions for single scale and 3 different aspect ratio boxes. We create base anchors for each feature map by calling this generateAnchor method for each size and aspect ratios pair that are defined for the 5 feature maps. The specific mechanism to create zero-centered base anchors is what we have seen already. We first create base anchors of area 1 and then convert them to base anchors of desired scale. And finally ensure that they are 0 centered. So cell anchors is just base anchors for all feature maps, which means it will be a list of 5, with each element being a list of coordinates for the 3 boxes of aspect ratio 0.5, 1 and 2. As an example, if we only see the 1:1 aspect ratio boxes, then this would be the cell anchors. For the first feature map, it will be of scale 32, so the 1:1 anchor box coordinates will be -16 for x1, y1 and 16 for x2, y2, making the area 32 times 32 square pixels. Similarly, for the last feature map, we had a scale of 512, so the 1:1 anchor box coordinates will be a tensor with x1, y1 being -256 and x2, y2 being 256, making the area 512 times 512 square pixels. And remember, this was because we initialized our anchor generator with scales 32, 64, 128, 256 and 512. Then we create a grid of anchors, where we use the strides to create shift values for the x1, y1 and x2, y2 coordinates of the anchors, same as we did in part 1. Only difference is that we are doing it for all 5 feature maps. Shifts will be according to stride, which means for the first feature map, the shifts will be 0, 4, 8, as it had a stride of 4. For the second feature map, it will be 0, 8, 16, as the second feature map had a stride of 8. And for the last feature map, it will be 0, 64, 128 and so on, as the stride for the last feature map was 64. Grid anchors method will add the shifts for each feature map to their respective base anchors, creating anchor boxes for all the feature maps. This anchors over all feature map will then be a list of these anchor boxes. So again, a list of 5, where the ith element is the anchor boxes at all locations for the ith feature map. Our first feature map was of size 200 x 256, and with each cell having 3 anchor boxes, this will give us 200 times 256 times 3, which equals 153600 anchors. Based on the same calculation, it will be 38,400, 9,600, 2,400 and 624 anchors for the other 4 feature maps. Finally, we duplicate these for all the batch images, so here for 2, and also for each image, concatenate all anchors for all feature maps together. So we had 2 images, hence anchors will be a list of 2, each being of shape 204624 x 4. This 204624 is nothing but the summation of number of anchors at all levels. This list of anchors is what is returned here. Now if you see, as of now our anchors is of different shape than objectness and prediction bounding box deltas. Anchors have all feature map levels concatenated together, whereas these two have each feature map levels output as different members of list. We are going to apply these prediction bounding box deltas to these anchors to convert anchors to proposals. So for that we need anchors and prediction box deltas to be of the same shape, which is what the next few lines and this concat box prediction function is supposed to do. Using the shape of objectness for each level, we compute the shape of anchors at all levels, which for each level will be 3 cross feature map height cross feature map width. Then this number of anchors per level will be the same 5 values that we saw earlier. Now let's see inside this concat box prediction layers method. In here, what we do is we first flatten the prediction for each level. So focusing only on classification scores for now, our current shape for each level is batch size cross number of anchors, which is 3, cross feature map height cross feature map width. we are permuting and making it batch size cross height times width times 3 cross 1. That's all that this permute and flatten method is doing. Similarly, box regression values for each feature map will be batch size cross height times width times 3 cross 4. At this point, this is what box CLS flattened looks like. Then we concatenate these along dimension 1 and we flatten to make CLS scores as 409248 cross 1 and box regression as 409248 cross 4. These are then returned and they now become objectness and prediction box deltas. After this, we apply the prediction regression deltas to all anchors. And since our anchors is a list of 2, each being of shape 204624 cross 4, so here when we concat on the first dimension to get concat boxes, we get a tensor of 409248 cross 4 shape, same as what the shape of box transformation predictions are, which is nothing but rel underscore codes here. And then like we saw in the previous video, we apply these transformations to convert anchors to proposals. This is same as the apply regression prediction to anchors or proposal method that we had seen in the last video, except in here we also divide by these weights to get dx, dy, dw and dh. And similarly later we'll see that while setting the targets, we'll multiply by these weights. These are just a mechanism to indicate to the model the relative importance of getting dx, dy, dw and dh right. But the default values for these weights for RPN are anyway 1, so it's effectively doing the same thing as our method. Finally, the return prediction boxes from this method is 409248 cross 4. And then after this reshape, and then the return proposals from here are again reshaped here. At this point, the proposals are 2 cross 204624 cross 4. So batch size cross total number of anchors including all feature maps cross 4. These are the proposals that are obtained after converting all anchor boxes based on the transformation predictions by RPN. Now we'll do all the filtering that we had seen within the filter proposals method in the last video. And this method gets the image sizes, which are the original sizes before zero padding. So this will be 800 cross 600 and 562 cross 1000. Proposals is batch size cross number of anchors cross 4. Objectness was batch size times number of anchors cross 1. And the number of anchors per level that we computed earlier. Now let's get inside this method. We first reshape objectness to be batch size cross number of anchors. So 2 cross 204624. Then we create a level identifier for each of these anchors by creating levels as a 2 cross 204624 tensor, where for both batch images, the first 153600 values will be 0, then next 38400 values will be 1, and the last 624 values will be 4. We are doing this because we'll use these level identifiers as class labels to do NMS per level independently. We first do per level filtering, where within this method, we loop over all the levels, so here 5, and for each level, we first select top 2000 boxes, because this RPN pre-NMS top n is 2000 as default when we are in training. But not all levels will have 2000 anchors. Like in our case, the last level only has 624. Then this method returns the indexes of those anchors which are amongst the top 2k scoring. So ultimately we get indexes for 8624 boxes for each image in the batch. 2000 for the first 4 feature map, so 8000, and 624 for the last level feature map. Then we select objectness scores, levels, and coordinates only for these filtered 8624 boxes for each image. Now for each image, we'll do further filtering within this loop, where we first clip the boxes to image boundary, and this is where we are using the non-zero padded shapes. Same implementation that we have been seeing of clamping proposal box coordinates between 0 and width and height. Then we remove small boxes, low scoring boxes with the default score threshold being 0.05. With the level identifier that we had created earlier for all anchor boxes, we use these identifiers as class labels, and then we do NMS independently per level. Finally, the top 2000 proposals for each image are returned. So from 8624, we are down to 2000 proposals for each image. Hence in our forward method, after this call, we have boxes as a list of 2 elements, each being a 2000 x 4 tensor. Now up till now, whatever steps of RPN that we have seen, we'll be doing them whether we are in training or inference mode. But if we are in training, we would additionally need to get targets for anchors and compute losses. Now remember, whatever filtering we did for objectness was inside this method. In here, we still have objectness as 409248 x 1 tensor. To compute the losses, we first assign targets to anchors, which is same as last video. Get the IOU matrix, match each anchor boxes to best possible ground truth box, and update labels as 1 for foreground, 0 for background, and -1 for to be ignored anchors. Only difference is that this caters to greater than 1 batch size by iterating over all the images in the batch. This method will return labels as a list where each element is labels for the 204624 anchors of that image. And matched ground truth boxes is also a list, and each elements are of the same shape as anchors. Then we get regression targets using the matched ground truth boxes and anchors, which internally does the same thing as previous video. Get anchor boxes CX, CY, width and height, then matched ground truth boxes CX, CY, width and height, and compute targets based on that. And like we had talked about earlier, this time we'll multiply by these box weights WX, WY, WW and WH. And again, all of these have a default value of 1 for RPN. The returned regression target is of the same shape as anchors because there are 4 transformation parameters for each anchor. Then after this, we'll compute the RPN loss. Foreground-background sampling does the same sampling as our implementation. It's just that it is doing sampling for each image in the batch. We get the number of positives, negatives, and randomly sample those number of positives and negative anchors and return masks for sampled positive and negative anchors. And once we are done sampling, we reshape objectness and also transform labels to be batch size times number of anchors in each image. So now objectness and labels are of the same shape. We also transform regression targets to batch size times number of anchors in each image cross 4, making it of the same shape as prediction bounding box deltas. Using the positive labeled proposals, we compute the localization loss as smooth L1 loss. And using all sampled indexes, we compute the classification loss using binary cross entropy. And this loss computation finishes the RPN part, where in the end, it returns the proposals, which will be 2000 proposals for each image as we are in training, and losses will be RPN objectness and RPN box regression loss. Now we go back to generalized RCNN, from where we went inside RPN and looked at everything in detail. And now we do the same for ROI part. The ROI heads forward method is called with the following arguments. Features. Now inside RPN we used only the values of features, which was a list. But here remember our features is a dictionary with 0, 1, 2, 3 and pool keys. And each key had a value as the feature map computation for the 0 padded image at different levels. The other argument is proposals by RPN, which were the boxes that were finally returned. So this will be a list with 2 elements, with each being a 2000 x 4 tensor. The third argument is image sizes for the images in the batch prior to 0 padding. And finally targets for each image in the batch. Going inside ROI heads forward method, after some validations, the first thing we do is sample from the RPN generated top 2000 proposals, but only if we are in training. Here we also add ground truth boxes to these proposals to ensure that even if none of the proposals returned by RPN are positive, the ROI head still would potentially learn to classify foreground objects correctly. So for these 2 images in the batch, we have 3 and 1 ground truth boxes, which means our number of proposals will now be 2003 and 2001. GT boxes and labels will also be a list of 2 elements, and the elements of GT boxes will be of shape 3 x 4 and 1 x 4. For each image, we then assign ground truth boxes and labels to the proposals for that image. This method is same as what we have been seeing for all the assignments, where we get IOU, and then the same matcher that we used in RPN is used here. Except our foreground and background IOU threshold is 0.5, which means nothing is ignored, unlike in RPN. So either a proposal will be labeled as one of the foreground classes, or it will be labeled as background. Apart from IOU thresholds, and the fact that we won't do any low quality matches, this is same as the RPN assignment method that we just saw. For the first image, because we have 3 ground truth boxes, matched indexes will be either 0, 1, 2 or -1. -1 if it's less than 0.5 IOU with all ground truth boxes. Then we do clamping. So all those proposals which had matched indexes as -1 will now be assigned to the 0th ground truth box. And these clamped assignment indexes will be used to set labels. And since the label assignment as of now for background proposals are incorrect, so we correct them by selecting these proposals which had matched indexes as -1 prior to clamping and set their labels as 0 or background class. This step is done for both the images in the batch, and finally the method returns a list of labels and a list of matched ground truth box indexes. Then we do same sampling as in RPN. Except the numerical values of how large the sample size is and the number of positive samples are different for ROI head. Now using these sampled indexes for both images, we select only the sampled proposals, their labels, and their matched ground truth box indexes, which we use to get their matched ground truth boxes. For these proposals, and based on their ground truth assignments, we get their regression targets, which will be used to compute localization loss later. And remember, matched ground truth boxes for all background proposals will just be the 0th ground truth box. But again, that's not an issue, as during computation of localization loss, we'll filter out those cases using labels. The target computation is exact same as RPN. Get the center X, center Y, width and height for both ground truth and proposal box, and then get the target dx, dy, dw and dh. Just notice that now the weights are not all 1, as we had seen in RPN, but instead they are 10, 10 and 5 for dx, dy, dw and dh respectively. At this point, our proposals will still be a list as before, but instead of each image having 2000 proposals, it will now only have 512, as that's the default sample size for ROI head. And the exact same will be the shape of regression targets. Labels will be same as proposals, except each element will be a 1D tensor with 512 values. And if we are not in training mode, then we wouldn't have done any sampling whatsoever. So whatever the proposals the RPN returned, say 2000, for all of those, we would perform the upcoming steps. For these proposals, we'll now extract features using the feature map of different levels, and then feed them through FC layers. For pooling, we use MultiScale ROI align. I won't be getting into ROI align part, as I'll cover that in mask RCNN video. So for now, we'll just focus on the MultiScale part. Whether the exact pooling strategy is ROI align or ROI pooling, we'll not be bothered about that and leave that as an implementation detail for now. The forward method for pooling gets the features, X hair, proposal boxes, and image shapes. The PyTorch code by default uses only the first 4 feature maps of strides 4, 8, 16, and 32. So in here, we do the filtering of keeping only the keys that were provided during ROI pooling initialization. So X filtered will be this list containing 4 elements, which will be feature maps for keys 0, 1, 2, and 3. The feature map for pool key would be completely ignored, and what to ignore and what to keep is initialized in the Faster RCNN class. Then after filtering, this method is called. This method creates an object that assigns appropriate level to each of the proposal boxes. This assigned level will be used to decide which level's feature map do we use to perform the ROI pooling, rather ROI align, to get features for that proposal box. Reason being, for smaller proposal boxes, it makes sense to do this pooling operation using earlier levels, which have finer features capable of handling these smaller sized objects. And for larger ones, we could use the later levels feature maps. Inside this method, based on the image sizes, which were sizes prior to 0 padding, we get the max dimension among all axes. So original input shape becomes 800 cross 1000. Then this infer scale is called for all feature maps, where inside infer scale, like the name says, we determine the scale for each feature map by dividing feature map size with original image size. Since the stride was 4, 8, all the way till 32, after this infer scale is called for all feature maps, we'll get scales as 0.25, 0.125, 0.0625, and 0.03125. Then using the scales and the fact that every level downsamples the image by 2, we determine the minimum and maximum levels as 2 and 5. Because for the first feature map, the scale was 0.25, So 2 levels of downsampling to get to 1 by 4. And for the last level, the scale was 1 by 32, so 5 levels of downsampling. Now we initialize this level mapper with the minimum and maximum levels. This level mapper will later be used to assign levels for each proposal box, from which we'll do the pooling to get features for that box. Later it's going to be called with proposal boxes, and essentially what we are going to do at that moment is compute the square root of area of each of these proposal boxes, and then compare them to a canonical size, which by default is 2 to 4, to decide which level that proposal box should be assigned to. This formulation of how to assign levels is provided in FPN paper. Don't worry if you don't know about this or FPN, as all of this I'll cover in a later video. All you really need to know for now is that ultimately this assigns each of these boxes to either 0, 1, 2 or 3 level, with the intuition that smaller boxes will be assigned to earlier levels and larger to later levels. With the scales and level mapper, we go inside this MultiScale ROI align method. Here the first thing we do is convert the proposals, which as of now were lists of 2 elements, each being 512 cross 4. We convert proposals to a 1024 cross 5 tensor, so concatenating the boxes for both the batch images and also adding an additional dimension which represents the batch index of the image that this proposal box belongs to. So ROIs will be 1024 cross 5, where for the first 512 ROIs, the first index will be 0, as these correspond to the first image, and for the next 512, the first index will be 1. This is needed because the PyTorch ROI align implementation requires ROIs to be of this shape, such that the first dimension for proposal box represents the batch index that this proposal box belongs to. Levels, as we had already seen, is the result of calling the level mapper object with all these proposal boxes to have their designated levels set. So levels will be a 1D tensor with 1024 values, and each value being either 0, 1, 2 or 3. This method is going to finally return this result, which will be a 1024 cross 256 cross 7 cross 7 tensor. 1024 because that's the number of ROIs, 256 as that's the channel dimension present in feature maps of all levels, and 7 cross 7 as that's the pooling output size. This is initialized as an all-zero tensor as of now. We then loop over all the different scales, their respective feature maps, and their respective levels, which was just 0, 1, 2 or 3. And inside the loop, we get the boxes that were mapped to this level and use the feature map of this level to compute the proposals for all these boxes by calling the PyTorch ROI align method. And finally update the result tensor for these proposal boxes. Doing this loop for all the scales will give us the features for all the 1024 ROI boxes, which will finally be returned. Then this box head, which is just 2 FC layers, will give us a 1024 dimensional feature for all the proposal boxes. And finally we have this box predictor, which again was initialized in Faster RCNN class, and it's just 2 sibling FC layers, one for classification and the other for box transformation regression. Classification layer has output as number of classes and gives us the classification logits, and the box transformation FC layer has output as number of classes times 4. And this gives us the transformation parameter prediction for all these proposal boxes for all classes. This entire set of steps is going to be common for both training as well as inference. But if we are in training, we need to additionally compute losses, and if we are in inference, we need to do some post-processing like applying the transformation to proposals, filtering, and NMS. Let's look at the training part first. Since as of now, labels is a list, and even regression targets is a list, so we first concatenate along the batch dimension to make both of them as a tensor with first dimension as 1024 to match the first dimension of CLS logits and predicted box transformation parameters. Then classification loss is just cross entropy between labels and logits. For localization, similar to RPN, we only use positive proposals by conditioning the label to be greater than 0. And for these positive proposals, we get the predicted transformation parameters for the ground truth class and use these to compute smooth L1 loss. If we are in inference mode, then this method will perform the responsibility of doing things like applying the transformation to proposals, filtering, NMS, and so on. So let's look inside this. Now in inference, we'll not be doing any sampling. So we won't really have just 512 proposal boxes for each image. We'll have all the boxes that RPN returns in inference mode. So maybe 2000. But let's assume that even in inference, at this point, we have 512 proposal boxes. Because that way we don't need to modify shapes of everything that we have worked with. Inside this method, we first apply the transformation prediction to all proposals to get prediction boxes. And since the transformation predictions are 1024 cross 84, whereas proposals is a list of 2 elements, each being a tensor of 512 cross 4, we first concat along the batch dimension to make concat underscore boxes also as 1024 cross 4. The actual transformation is same as RPN, where we applied transformation prediction to all anchors to get proposal boxes. Except here, because we have transformation prediction for all the classes, we'll be transforming our 1024 cross 4 proposal boxes to 1024 cross 21 cross 4 prediction boxes. So using the transformation for each class to convert each of the proposal boxes to 21 prediction boxes. But the rest of the computation is same, getting the CX, CY, width and height from x1, y1 and x2, y2 of proposals, and then apply the dx, dy, dw and dh predictions. So our prediction boxes are 1024 cross 21 cross 4. We then softmax on class logits to get classification probabilities for the predicted boxes. Now we need to do filtering like NMS for each image separately. So we first convert the prediction boxes back to a list of 2, with each element being a tensor of 512 cross 21 cross 4 shape, representing the prediction boxes for both the batch images. Then for each image, we start doing the filtering. We first clamp the boxes to image boundary, again using the sizes prior to 0 padding. Then we create labels as a 512 cross 21 tensor by first creating a tensor with values from 0 to 20 and replicating it for as many boxes as we have for this image. Now since we don't really care about the boxes that have predicted class label as background, so we get rid of the background scores, boxes and labels by removing the first index. After that, we combine all the boxes together. So as of now, we'll have 512 times 21 boxes for each image. Each box assigned a certain score based on the classification probability after softmax, and a label between 0 to 20, actually 1 to 20, as we remove the background labeled prediction boxes. We then remove the low scoring boxes and also remove small boxes, same as RPN, by ensuring that the width and height are greater than some minimum threshold and filtering those boxes out that don't meet this criteria. Then we do NMS, where for NMS, the labels will be used as classes to perform suppression independently per class. This allows the same proposal box to generate predictions for multiple classes. After NMS, we further only keep top k boxes per image, where by default k is 100. So after doing this loop for both images, we would be having top 100 boxes for both of them. So boxes returned here will be a list of 2 elements, each being 100 cross 4, and scores and labels would also be a list of 2, but each element being a 1D tensor with 100 values. Scores is the classification probability after softmax, and labels are the predicted class index for those boxes. So this is all for the ROI head part. Now finally the last part of the forward method of generalized RCNN. These boxes that we have were for the images after they were resized to 600 cross 1000 dimension. But we need boxes for the original image dimension, so we need to do that transformation. Our original image sizes in this case were 500 cross 375 and 281 cross 500. Image shapes was 800 cross 600 and 562 cross 1000. And the boxes returned by ROI head correspond to this dimension. So we call this post-process method in generalized RCNN transform, where for each image we get the original size by new size ratio and multiply the predicted box coordinates with this ratio. This will transform all the predicted boxes back to the original image dimension. And that covers about everything that is happening inside Faster RCNN PyTorch codebase. The forward method finally will return the losses, which would be the classification and localization for both RPN and Fast RCNN, and detections, which are the boxes, their scores, and their class label. If we want to use this PyTorch codebase to train a faster RCNN model on our own dataset, we have two options. We can either fine-tune a pre-trained faster RCNN checkpoint, or we provide the implementations of different components like the trained backbone, AnchorGenerator, and so on, and PyTorch code plugs in these components and gives us our own version of faster RCNN that we can train from scratch on our own dataset. Let's quickly see both of those. For both, our dataset class is same as last video, which just returns the image and targets for the image as a dictionary, with boxes and labels as keys. But there are a few changes in the training script. While instantiating our data loader, we can now provide it a batch size greater than 1. If we want to use the pre-trained faster RCNN with Resnet50 FPN, then we instantiate our model using this method, which allows us to pass in arguments for things like whether we need the pre-trained version or not, how many layers of backbone need to be trainable, and so on, and also any argument that the faster RCNN class expects. So be it the RPN threshold values, NMS values, or whatever. Like here, I am using it to specify the min and max size according to the faster RCNN paper. Now the returned faster RCNN model will be one that has been trained on Coco dataset. So if we are working on our own dataset, we would be having different classes, and hence the ROI heads classification and box FC layers need to be changed. So we'll modify the prediction FC layers using the box predictor field of ROI heads. Note that we are still keeping the two MLP head layers, and this is only changing the final classification and box regression FC layers in ROI head. So for initializing the new box predictor layer, we need the FC layer dimension and the number of classes. The FC layer dimension we extract from the already present CLS layer, and since we are training on VOC dataset, the number of classes we set as 21. This will give us a pre-trained faster RCNN with prediction FC layers initialized from scratch that we can fine-tune on our own dataset. Now rather than fine-tuning this pre-trained faster RCNN model, as I mentioned, we could also build a faster RCNN by plugging in different components and train it from scratch on our dataset. So for that, we have to first create a backbone. And here I am using a Resnet34 backbone that is pre-trained on ImageNet. I am also removing the last few layers to have the final stride as 16, just to mimic what we did with VGG16 in our last video. The PyTorch code expects out channels to be present as a field of backbone, as then it can use that for creating the RPN prediction layers and for creating the FC layers on detection side. So we add that, which in our case of Resnet34 is 256. And then we specify the ROI align and AnchorGenerator. For AnchorGenerator, you can specify the scale as well as aspect ratios of anchor boxes in arguments. Here I don't do that because the default values are anyway what we want to use. So like the authors, we are going to use single scale feature map and use anchor boxes of 3 scales and 3 aspect ratios. Then we create our faster RCNN class using these different components that we initialized. Here also, you can pass the min size, max size, and basically all the arguments that faster RCNN class allows you to create the model that you desire. Everything else is the same for both the cases, which in turn is same as our previous video's training code. As I mentioned in the last video, using the PyTorch pre-trained faster RCNN model, you would be able to get more than 75% MAP on VOC 2007 very quickly. And with further training and tuning, one should be able to cross 80% MAP as well. So this was everything that I wanted to cover for faster RCNN implementation. In this part, we covered the PyTorch faster RCNN codebase, and in the previous part 1, we implemented faster RCNN step by step. I am hoping that both these parts would have been of some help to you in your attempt to understand faster RCNN. Thank you so much for watching this video right till the end. Up next on this series, I am going to start getting into one-stage detection methods like YOLO, SSD, and so on. So see you then.